I have to admit, sometimes I see something and jump to conclusions. I get an idea in my head, and instead of stepping back and taking a new fresh look at the problem, I just keep plowing ahead. Like this waveform. It was measured with the scope probe using the spring as ground, so no real loop at the probe tip to pick up much. So I think somehow the switching spikes are getting into the MOSFET amp and causing it to oscillate. I've been kind of fixated on that theory. And I didn't want to start the new power supply until I found out how those switching spikes were getting into the MOSFET amp. So the hunt was on. The first thing I did was try putting some ferrite on the lines from the power supply. Made absolutely no difference, and I have to say I was a bit surprised at that. Well, if it's not in the wiring, the power supply is close to the heatsink, and the heatsink is directly connected to the drain of the power MOSFET. So I'm going to try and move the power supply. This has got to be an extremely long shot, but it is easy to try. And no difference. Here is where I did notice that if I squeezed around the switching transformer with my fingers, it would lower the noise spikes a bit. It doesn't seem to be a radiated problem, so I wasn't sure why that was. And at this point, I'm still thinking about the noise spikes getting into the MOSFET amp through the ground circuit. I just don't know how it's getting there. I do have a 220 picofarad capacitor across the power input ground and the power output ground. And since that's connected to ground, and I'm at a loss as to what to try next, and the switching noise seems to be just about everywhere, I'm going to pull that out and see what it does. Well, that really increased the amplitude of the switching spikes. But how would that have really any effect on the noise in the ground circuit of the MOSFET amps? It shouldn't. I don't have anything connected to the load. Well, yes, I do. When I'm taking a measurement with the scope, I have the scope connected to the load. And I can see that capacitor having an effect on the noise between the scope ground and my power supply output ground. And that may be where this is coming from. The noise is larger across the banana jack terminals than the bus bar terminals, but the banana jack terminals have about 3 inches of wire on each terminal connected to the bus bar, so the bus bar is much closer to a short. But even shorted, there is still quite a bit of signal there. I think this is being picked up between the scope ground and probably any point on the supply side of my power supply. I have overlooked this entirely. What a mistake. A lot of complications with the switching power supply. Yeah, it's not radiating from the load terminals. Let me put the cap back across the grounds. If this is noise across the scope ground to my power supply output, it's not causing my 200 to 300 millivolt, 125 kilohertz ripple in the output of the load. I do want to double check, so I'm going to double the cap, put another 220 picofarad in, and see if it lowers the noise. Yep, so that's not my problem. The noise is there, and I do need to try and reduce it. There's too much electrical noise all around, so I don't want to add even more to it. I would guess most of this is coming from the primary to secondary capacitance in my transformer. Not real sure about that. But this power supply is getting replaced, so I'm not going to worry about it for this one. I will test for this on the next power supply, though. But 200 to 400 millivolts of 125 kilohertz ripple is being induced in the output of the load. So then where is that coming from? I think I've eliminated the idea that the switching spikes are causing the MOSFET amp to ring. So that means I've got to be getting some 125 kilohertz ripple in some place sensitive. And that word sensitive really got me thinking about the output rails of the power supply, and just how sensitive are the circuits I'm supplying. I'm pretty sure the 3.3 volt line is going to be the most sensitive to voltage ripple. The DAC output will follow the 3.3 volt rail, and that is the drive for the MOSFET amps. The least significant bit of the DAC is about an 800 microvolt step. So I figured if I had noise less than 400 microvolts, I would probably be okay. I don't think that was a good assumption now. But I do have a voltage regulator on the 3.3 volt rail with very low noise and a high power supply rejection ratio. It shows better than 60 decibel ripple rejection at 100 kilohertz. So if I had 30 millivolts of ripple coming in, should only have 30 microvolts of ripple going out. I think 30 microvolts will be fine, but I'm not sure now. Now the 12-volt rail doesn't have a low noise regulator, doesn't have a linear regulator at all. So the only ripple rejection on the 12-volt rail is the filters on the MOSFET amp modules and the PSRR of the op amps being used. Here, the LM7321 that drives the power MOSFET, right at 40 decibels. So 30 millivolts of ripple on the positive supply would be 300 microvolts on the output. Here, the OPA 2189 that drives the LM7321, positive supply is above 40 decibels. Negative supply is below 20 decibels at 125 kilohertz. And now I have a negative supply, so that may even add a bit to it. After looking at the PSRR of the op amps, I think the first thing I'm going to try is add a bit of extra filtering to the 12-volt rail. See what it does. I'm going to make up a small little filter circuit, 2 10 microfarad capacitors and a 10 microhenry coil. Had a few of these PC boards left over from the DualSense charging cradle mod. If I'm very careful with the inductor placement, these will work just fine. So I'm going to install this in the 12-volt line right out of the power supply. Here's the waveform at the load terminals with a 1 amp load. About 70 millivolts of 125 kilohertz ripple. That is really a big difference. Compared to this waveform of the same 1 amp load before the added filter, around 250 millivolts. So adding a tiny filter circuit reduced the ripple to less than a third of what it was. I think I have found what I was hunting for. Adding a filter to the 3.3 volt rail looks like it may have reduced it a little. Of course, the 3.3 volt rail is pulling about 3 times the current of the 12 volt rail, so my little filter won't have as large a ripple reduction. I'm glad I followed up on these items. I think it will help me build a much better power supply version 2. The switching noise spikes, while I want to reduce them, are not really causing me any problem. Not realizing I was picking them up between grounds has cost me quite a few hours of frustration, for what turns out to be a very simple problem. And that problem? I need cleaner power supply rails. It's simply the 125 kHz ripple from the power supply getting into the MOSFET amp. And that should have been the first thing I looked at. I'm not sure what made me think the switching spikes were causing the MOSFET amps to ring. Just a delusional idea I became fixated on, I guess. But I think I'm on the right track now. I have a pretty good idea of where to head with the new power supply design. A linear regulator for the 12 volts to the MOSFET amps, that's for sure. I'm thinking I might do double linear regulation for the 3.3 volt rail. Might as well do it for the plus and negative 5 volt supplies while I'm at it. Or at least plan on it. May not have to implement it. So definitely the new power supply next. And oh joy, more transformer winding. Thank you for watching.